All right, I think we'll go ahead and get started with our seminar for this month. Again, this is Iowa Nutrient Research Center Spring Seminar Series, and welcome everybody to this month. We have Dr. Chad Penn, that's a soil chemist with USDA Agricultural Research Service in West Lafayette, Indiana, talking with us today. Just as a reminder, this is the fourth in the series of our Focus on Phosphorus seminars. And so we had Justin Chafin from Stone Lab and the Ohio Sea Grant of the Ohio State University talking in January. Barbara Cade Menon from Saskatchewan talking from the Swift Current Research and Development Center talking in February. For those of us at Iowa State University, our own Antonio Mallarino talking in March, and now Dr. Penn with us. And so all of those are archived on the Iowa Nutrient Research Center website, as well as this one will be archived as well, as long as my recording works out okay. And so far it seems to be working. So really fortunate to have Dr. Penn with us today talking about removing dissolved phosphorus from flowing water with P removal structures, the good, the bad, and the ugly. So we've talked a lot about infield and reducing runoff phosphorus, but emerging questions about dissolved phosphorus through tile drainage lines, other forms of dissolved phosphorus losses, and what we do about that. So with that, looking forward to Dr. Penn's presentation, and I'll turn it over to you, Chad.
All right, thank you. Let me start my screen share. All right, are we good?
Yep, that looks great.
Title slide. Okay.
Yep.
All right. Thanks. I appreciate this this opportunity. I'm looking forward this summer. I'll be out there for the drainage conference, so I'm looking forward to be able to meet some of you in person. I'm not going to talk about phosphorus and eutrophication. You guys already know about that. I'm going to jump right into it with a phosphorus removal structure. The target of the phosphorus removal structure is dissolved phosphorus. And I say that specifically to differentiate it from particulate phosphorus. Not only is the target dissolved phosphorus, but it's dissolved phosphorus that's coming from high P soils, from legacy P soils. And I say that to differentiate it from dissolved phosphorus that's coming from recent manure or fertilizer applications. We call that incidental losses of phosphorus. The target of this is dissolved P coming from these legacy P soils. And by legacy P soils, I know that's a somewhat ambiguous term here, but in this case, I'm defining it as soils that have at least 100 milligrams per kilogram of malic 3 phosphorus. So why are we focusing on dissolved phosphorus? It's because it's a more potent eutrophication agent than particulate phosphorus, mainly because aquatic organisms can immediately take up dissolved phosphorus from water as soon as it reaches a water body. That's not true for particulate phosphorus. That phosphorus that's bound onto a sediment particle, its bioavailability is going to vary depending on the characteristics of that soil particle, the concentration of phosphorus within the overlying water column. So part of the phosphorus may desorb. Sometimes those sediment particles can actually absorb phosphorus from the water column. But dissolved phosphorus, as soon as it hits the organisms, the plants can start taking it up. Why specifically are we targeting dissolved P from high P soils, from legacy phosphorus soils? The reason why is because those soils tend to stay high in phosphorus and to behave as sources of dissolved phosphorus for a long time. That makes it totally different from nitrogen, because soil phosphorus is very strongly buffered. So if you build up your soil test P too high, it will stay high for a long time. This is some data from over on the eastern shore of Maryland, where they built up soils purposely all the way up to about 600 milligrams per kilogram of malic 3. At that point, they ceased all application and then draw down the soil with corn, wheat, beans rotation for several years. And ultimately what they found was that if the soils were initially at around 200 to 300 milligrams per kilogram, then it would take 20 to 30 years of drawdown to bring them back down to agronomic optimum levels. And that's with no further P applications. So if you got a high P soil, it can be a long-term problem. So all that time while you're trying to draw down the soil, bring that soil test P level down, every time you get a flow event, you're going to lose a little bit of dissolved P every time. So during that period, for drawdown, while the soil P is being decreased, this was the impetus to develop the P removal structures to try and filter that phosphorus during that long time period of drawdown. So, what in theory, the P removal structure, it's very simple. It's just a big, large landscape scale filter. You have high dissolved P concentrations channeled into it, flowing into it, and you've got a media contained in it that has a high affinity for phosphorus that binds it by some mechanism or another, depending on the media, precipitation, ligand exchange usually, and then low phosphorus water comes out. So like I said, in theory, it's very simple, but designing one to meet certain goals is a bit more involved. And we'll talk some about that. So there's 3 necessary components to a phosphorus removal structure. The most obvious one is that you need to have a filter media, what I call a PSM, a phosphorus sorption material, in a sufficient quantity. You have to have enough of it to be able to handle an appreciable load for that site. So they need to be custom designed for each site, and they need to be designed to handle a sufficient flow rate for that site and at a sufficient contact time. So the majority of dissolved phosphorus is lost at the largest flow events, the highest flow rates. The number often thrown around is that 90% of the load is lost from like 2 or 3 of the biggest events of the year. And so you need to be able to treat these things to have water flow through them. If water doesn't flow through them, you're not treating the phosphorus. Water can't just flow over them. It has to flow through the media and be in contact with that media for a sufficient amount of time. These are all things that go into a proper design. And they also have to be designed and constructed so that you have the ability to retain that media. You can't just throw it in a waterway. You have to be able to retain that media and then be able to replace the PSM at the appropriate time when it's no longer effective or performing to what you need it to do. So knowing that, those 3 main components, you can, P removal structures can be pretty diverse in appearance. We've built a whole lot of different types under different scenarios, and if you meet those 3 components, you've got a P removal structure in some way, shape, or form. And later I'm going to give you a survey, just some examples of different types that we've built. So at the heart of the P removal structure, the filter media itself, the phosphorus sorption materials, the PSMs, a lot of them are industrial byproducts. I like to use them industrial byproducts because they're highly available, they're very inexpensive, and they work pretty well. However, they do need to be screened for safety to make sure that they don't contain excessive soluble amounts of trace metals. Some of my favorite materials are metal filings. We've used a lot of steel slag in the past. There's also manufactured P sorption materials. I'll say more about that in a second. So these manufactured P sorption materials, they tend to be very efficient. That is P removal on a per unit weight basis. They're pretty good, but they're very expensive. Almost all of them are pretty much cost prohibitive. There's some different examples. Some are made in Ohio that come from all kinds of places. ActiGuard from Accent Solutions, I found, tends to be probably the most cost effective, but they're usually, some of them are calcium-based products, some of them are magnesium. Most of them are iron and aluminum oxide-based materials. In general, the iron and the aluminum oxide-based materials for all PSMs, whether they're manufactured or not, tend to be the most efficient. compared to calcium. That's due to the type of P sorption mechanism that is utilized by them. They also tend to remove P faster than your calcium and magnesium based materials. So the physical components of a P removal structure, normally what you have is some sort of and there's some exceptions to this, and you'll see that, but you normally have a distribution system of some sort for distributing the water for the untreated inflow water, usually perforated pipes, although sometimes, in some cases, you can have standing water that's evenly distributed, and you'll see an example of that. You need to have your bed of PSMs, the filter media, and then you need to have another set of drainage or collection pipes, perforated pipes, for removing the treated water from the structures. Obviously the treated water has to be removed so that the untreated water can continue to flow into it. So we normally use perforated pipe for that. This is just kind of a generic representation of that here. This one is shown for a subsurface filter unit, although an above ground unit would have similar components. You've got, and this one flows from the top down. We've built them and designed them to flow from the bottom up as well. It just depends on your situation. But here you have water coming in at the top, flowing down through the media, filtered out, and then collected through another set of perforated pipe where that treated water is then carried out. So this is covered. There's a NRCS standard for it. It's cost shared. That's standard number 782. It's not adopted. It's not in all states. Each state has the opportunity to adopt it. I don't know if it's in Iowa or not. We do have it cost shares as part of EQIP in Indiana, Ohio, New York, Pennsylvania, Maryland, Oklahoma, Texas, Wisconsin. There's probably some others, Florida, I think, probably some other states. I don't know about. I don't know about Iowa, but it's standard number 782. Okay, so like I said, while the structures are really simple in theory and how they work, just a big filter, designing them is much more involved. And so we developed a software called PTRAP, Phosphorus Transport Reduction App, to aid in this process. And if we have time, I'll give you a brief, very brief demonstration of that. But you need to know some things, some general inputs, like any tool, to make a design. So you need to know something about your site, hydrology. You need to have some idea of the peak flow rate that you want to be able to handle. You need to know something about the annual flow volume at your site, the dissolved P level, obviously, and the maximum footprint that you're willing to sacrifice to build it. And then you have to choose a target. How much phosphorus, that is, as a cumulative percentage, do you want to remove over what time period, over what lifetime? These are choices by the designer. And then, of course, you need to have some characterization on the filter media that you're going to use. Obviously, its ability to remove phosphorus. And we have that's characterized through a flow-through test, and that I realize most people don't have that sort of data. So I've measured. I've got probably nearly 1,000 different phosphorus removal curves for different medias at different concentrations and retention times, contact times that are available to be used within the software. People can just look them up if they don't have it, if their material is known. If you do have a material that's never been tested, or you don't have that information for the pure removal curve by flow through method, you can send it to me and I'll measure it, because I'm always looking for new materials. I just add them to the library. People send me, from years, people have been sending me materials from all around the world, and I'm happy to measure them. They need to be characterized for safety, and also physical properties, really important, because they got to conduct water. So hydraulic conductivity, block density, porosity, things like that. So you put all that in, and then as an output, you get your site-specific design specs. How much of your filter material will you need to meet the goals that you specified for your site and handle the flow rate and the contact time that you specified? So what mass and how should that mass of your filter media be oriented to do this? And it'll also tell you what pipe requirement, what pipe you need to be able to meet your goals. This is just a screenshot, what it looks like. Easiest way to get to it, it's a USDA ARS product. It's free. So easiest way to get to it, just Google P-trap phosphorus, and you'll come to the page for it, the landing page for it. And you click on the P-trap icon, and you'll go right to it. Okay, before I give you an example, several examples, what some different structures look like. First thing I want to say is that if a site's worth treating, it's going to require a large mass of filter media, of phosphorus sorption materials, PSMs. Why is that? We're talking about not pounds of filter media that's needed. We're talking about tons. And the reason why is because your filter needs to be able to handle a high flow rate. Okay, and the only way to handle a high flow rate, you can't just take all the flow coming off a single field and think that you're going to be able to channel it through a little cartridge filter stuck on the end of a tile drain pipe. I wish that were true, but it's impossible. So they need to be big because you need to handle a high flow rate. That's what most of your phosphorus is delivered anyway. And they need to be large so that they have a sufficient contact time. And they also need to be large so that they have a useful lifetime. You want these things to last years, not weeks. So I wish I could tell you that we can just make little cartridge filters in small modular boxes with 5-gallon buckets sitting in them, but it's just not true. It sounds really nice, you got something that's portable, easy to install, but the problem is those only work in very limited situations. So limited that you got to ask yourself, is it even worth using them? And I say that in limited situations because they can't handle hardly any flow rate. They can't handle much of a load. So you got to ask yourself, is it really worth even putting in small ones? And the reason why they're so limited is because they have such a small amount of PSM. So they have poor flow rates. They can't handle much of the load of the total mass of dissolved phosphorus coming off of the field. Just doesn't make sense. They need to be built very large. Same thing for filter socks. I wish, I'll put it this way, if it were that easy that we could just use little boxes or filter socks, we wouldn't have a problem in the first place. Filter socks, it sounds real nice, but you don't have, you've got a very limited mass of media in a filter sock, very limited contact between the water and the media, and very limited contact time. So filter socks, no good. Okay, so currently the technology, it's effective, but I'm a researcher, so I'm going to say it can always be improved. We've built a lot of these things over the years throughout the world. I help people design them. Right now, we're more in dissemination stage, so I'm doing things like trying to get the software out, working with INRC and making some training videos to train people how to design and build them themselves, so that it can spread and people can actually start implementing them more. But like I said, they can always be better. So my current research on those is dedicated to decreasing the costs and improving the efficiency of the Pmobile structures. How are they different from nitrogen bioreactors? I could summarize in one sentence and say that nitrogen bioreactors remove nitrogen by biological means, and we're removing phosphorus by chemical reactions. Main difference then practically is flow rates and water volume. So remember, with phosphorus, we want to capture the highest flow rates. That's what's delivering most of the dissolved phosphorus. Therefore, you have to build structures that have a short retention time. So retention time, we're talking about seconds to minutes, not hours. Your nitrogen bioreactors have several hours of retention time because they're removing nitrogen biologically. Again, we want to handle the high flow rates because that's what delivers the most phosphorus. How are they different from treatment wetlands? Wetlands are really good at reducing particulate phosphorus, but not dissolved phosphorus. They drop out a lot of sediment. In fact, there's several researchers now, they say that treatment wetlands can actually increase dissolved phosphorus. But regardless, they're not, you're not reducing dissolved phosphorus with the treatment wetland, but you're doing good on particulate feed. So now a lot of people are talking about combining wetlands in combination with the Pmobile structure. And I'm working with several folks in Wisconsin and Ohio to try building some of these, where the overflow from these treatment wetlands on the back end of it, then we'll take that overflow water and run it through a Pmobile structure to be able to remove the dissolved phosphorus. A lot of interest from the Great Lakes Commission on that, and the U.S. Army Corps of Engineers is really into that as well. Okay, show you some examples of what some structures look like. This is one we built in Oklahoma on a poultry farm. Probably had like 14 different poultry barns on it, and a lot of spilled litter outside of those barns. The runoff from those would accumulate. It was located fairly close to a creek about 100 yards away. And so we built a Pmobile structure to intercept that water. We used some berms to channel that water into it. In this case, we're using 40 tons of a treated slag. So this is a steel slag that we coated with aluminum. So we have a series of perforated pipe at the surface to distribute the water underneath it, another set of perforated pipe to gather the treated water, and then out through the expanded metal to be drained out. This handled around 1,000 gallons per minute, and it cost about $5,000. So I call this, by the way, I refer to this as the confined bed structure. Build them on the surface. Something very similar to that is the ditch filter. We build a bunch of these on the eastern shore of Maryland, maybe 12 or 15 of them. And it's very similar to the confined bed, except instead of building something to confine your filter media, the ditches hold it for you. So it allows a large amount of material to be used. And most of the ones we built there, we used flue gas gypsum was readily available, and a sieved, highly sieved steel slag. And we were putting in anywhere between like 80 and 120 tons. They're easy to build. So, let me back up. So similar though, you've got in your ditch, you've got your perforated pipe connected to a drainage manifold to take the water, treated water out. This gets backfilled with your media. In this case, we are also using a flow control structure to build some head on it. And then as water comes down that ditch, it's held back by the flow control structure or a weir of some sort. Water infiltrates through the media into those perforated pipe and back out. That's what it looks like after construction during a flow of it. So that water is now held here, flowing, infiltrating through the media, and the treated water is taken away. They're fairly low cost, less than $4,000, easy to build. Works good for ditches. I don't recommend it for all ditches. In fact, I only recommend it for primary on-farm ditches in the Midwest. And the problem is that if on the secondary ditches, they fill up with water and they'll likely wash out all the PSMs. But for the secondary receiving ditches, I would consider a ditch bypass filter, something like this for your primary, secondary ditches. Divert the water from the ditch and basically construct a small stormwater basin and use that, build that into your Pmobile structure, and that treated water can then be diverted back into it. That's one way to do it. I've never built one like this. That's one option. Another thing you could do for a non-primary ditch is to build it directly within the ditch, but use a wheat pipe to allow the ditch to drain all the base flow during your regular flow, non-storm flow events. And then with the dam, so here we have the inlet, the blue pipe is your wheat pipe that just takes away, lets the base flow just pass through it. You've got a dam here, so during the flow event, water level raises up in the ditch where it enters the inflow pipes, distributed through the media, drains down through and out as normal. So this allows the unit to treat storm flow, that's where you get most of your dissolved phosphorus transported, not the base flow. But it also allows you to not back up water upstream by if you just had a dam and did not allow that base flow to pass through. Blind inlets are not a Pmobile structure, but they can be modified to be a pre-removal structure. So first, I'll briefly explain what a blind inlet is. They are used to drain surface depressions in fields. So imagine normally in your area you call them potholes. So imagine those, they accumulate a lot of water. You have a lot of standing water. So farmers are often install these Hickenbottom riser pipes within there to drain it. And the problem with those is they're a short circuit connecting surface water directly to the tile drain. And all the sediment that's up in the surface is just being shot down right into your tile drain system and lost that way. So what farmers will do is they'll replace that Hickenbottom riser pipe with a layer of some perforated pipe that's backfilled with gravel. We call that a blind inlet. So then they're still able to drain that depression or that pothole, but the water has to infiltrate first through the layer of gravel or sand, and that filters out a lot of the sediment, takes out a lot of your particulate phosphorus very well. We had one we monitored for 12 years, and it removed about 40% over 12 years of particulate phosphorus, but it did pretty much nothing for dissolved P. And you wouldn't expect it to, because it's just gravel. It's not going to absorb dissolved phosphorus. Now, if you replace that gravel or amend it with a P-sorption material, then you have it becomes a phosphorus removal structure. Here's just a cutaway of the blind inlet to show you what it is. You've got your depression, your pothole, runoff flows into it, and you've got your layer of gravel that traps the sediment, layer of perforated pipe underneath it that captures that water, and that's connected to your tile system and lets that water, so you're still able to drain that depression. Okay, now if you replace this gravel or amend it with a P removal media, then it has all the components of a P removal structure at that point. So first one we did on that was we replaced our regular local limestone gravel with a sieve steel slag, and it worked very well. We removed, it's only treating surface water, of course, but it removed, by 2018, it removed 46% of the dissolved P load. It also removed some glyphosate and some dicamba, other things as well. Last summer, we replaced this steel slag media with a metal shavings gravel mixture for increased performance. These are cheap. We were building them before for like $1,500. This last one cost us about $3,000. Here's the media we replaced it with. One that you have some close to you locally there, I'm going to mention in a second, but here's your mixture of your metal shavings mixed with the gravel, about 8%. This is what it looked like when it was completed. Here's one that you have there. This was a project led by Dr. Sapir and Dr. Kalita on the infamous, if I'm correct, it's the Walnut Depression pothole out there near you guys, south of Ames. And so it's a blind inlet, but we specially designed it using a gravel metal shavings mixture to allow it to additionally remove dissolved P, not just particulate P. So in doing that, this blind inlet became a P removal structure. It was installed around July 2021. And so it's predicted to remove about 40% of the cumulative 15-year dissolved P load based on the current loading. So Amy and Michelle have monitored this depression for years. So they knew exactly when we sat down and designed it, they knew exactly what the flow weighted concentration of dissolved P was. It made my life a lot easier. They knew what the annual flow volume was. And so we were able to do a design actually pretty easy. And if we have time, I'll show you a brief demonstration of how we did that using the software. Another similar thing is a bioretention cell. So again, a bioretention cell by itself is not a P removal structure, but if you amend it or use a PSM material, it becomes a pea removal structure. And essentially a bioretention cell is nothing more than an urban blind inlet. It's the exact same principle as a blind inlet, except it's basically your stormwater basins converted to remove sediment. If you mend it with a PSM, it removes phosphorus as well. Tile drains are another. This is a prime target. This is one of the reasons I was hired by ARS, was to bring pea removal structures to the Midwest to try and use on tile drains. Before I came here, when I was in Oklahoma, I was working, doing this only on surface runoff. Same thing in the Chesapeake Bay. We're building the Chesapeake Bay watershed for surface runoff. Came here and tried to adapt it to tile drains, and it was really, really difficult. But I think we finally got there. Learned a lot in doing that, making a lot of mistakes. We learned a lot from that. But essentially, the principle is the same. You know, you've got essentially a buried bed of media that you plumb your tile drain into. You've got a distribution system to distribute water into it, drains through the media and then back out. We can design these to flow from the bottom up, depending on your situation, or to drain from the top down. Depends on the amount of hydraulic head at your site. Depends on where you're able to drain these things. Sometimes your only option is to do a bottom up. Here's one we built in Waterloo, Indiana. This one flowed from the bottom up. We also built a blind inlet there and plumbed it into it. So this particular tile drain filter was treating not only the subsurface tile drain, but also all the surface water at the site that was accumulating at the blind inlet. In this particular case, we used 36 tons of a normal slag. It cost about $11,000. It worked okay for about a year. And one thing we learned, a valuable lesson on this and a couple other ones, and you'll hear me say it again, is do not use regular slag, that is blast furnace slag or electric arc furnace slag, for tile drains. Only use it to treat surface runoff. And the reason why is because the chemistry of tile drainage is much different than surface runoff. Tile drainage, in short, kills slag. In fact, it kills all calcium-based phosphorus sorption material because it contains a lot more bicarbonate than surface water due to all the respiration activity in the soil. And it'll end up clogging up and it won't remove much phosphorus either. So as far as slag goes, if it's a regular slag, not coated with aluminum or anything like that, you only want to use it on the surface. Works good for blind inlets, not for tile drainage. Here's another subsurface one we built in Northeast Ohio. So here I've pictured this is the drainage layer of perforated pipe before it got backfilled. That's the drain, where the drainage manifold where it all accumulates and goes out. And then here it is backfilled with slag. And then this is the distribution pipe sitting on top of it. We use flow control structures often in combination with these things to give us a little bit more control of the system. And then this got backfilled. We cover this with a tarp and then backfilled it with soil. Here's another one for a tile drain filter. This one, we've built several in tanks. Some people like to have them in tanks. Tanks are nice when you are using an expensive media that you want to regenerate, recharge it. We've developed a regeneration process for stripping phosphorus off of certain media, especially manufactured media. If you're spending a lot of money in manufactured media, sometimes it's worth it to put in a tank, especially if you can regenerate it. This was one of those cases. We use flow control structure to control the flow into it and also act as a diversion, overflow when necessary. And this particular unit, we use an activated alumina. It was designed to remove 40% of the 10-year load. It cost us about $12,000. Used 2 tons of activated alumina. The thing about the tanks is because they're not as large, you can't handle quite as high of a flow rate as if you make a giant bed. I mentioned the process for stripping phosphorus off of some of these materials. If you're using a material that's worthwhile of doing that, expensive manufactured material, quite frankly, then sometimes it's worth it to strip the phosphorus off of it when it's become saturated. So we developed a process to do that using potassium hydroxide and recirculate. You can do it in situ and recirculate that solution through it, stripping the phosphorus off. Not because you want the phosphorus as fertilizer, because quite frankly, it's not very much phosphorus in the realm of agronomic needs. You're only losing a tiny, tiny bit of phosphorus from these fields. Agronomically, it's inconsequential, but to the aquatic systems, it's quite devastating. So the benefit of this is that you don't have to buy new media. It's not that, oh wow, I have 10 pounds of phosphorus, whoop-de-doo, that's not even enough to fertilize 1 acre with. So it can save money in the long term if you're using a manufactured media. Probably my favorite material right now, most cost effective, most bang for your buck, are steel metal shavings. And I get these from the metal recycling plants. This is what Dr. Kalita, Dr. Sapir used with their graduate student, Adam, and building that blind inlet. And it's very simple. Those metal shavings are steel, they rust, they produce iron oxide, and phosphorus has a strong affinity for that iron oxide. You can get them fairly cheap, $300 per ton for the metal. You mix it 8% metal by weight with a gravel. You can use sand, but preferably a good clean pea gravel works much better. And they will remove a pile of phosphorus per unit mass, and especially for the cost. This is what I've been recommending in most cases to people if they have that material available to them. Here's an example where we use that media, 8% metal shavings mixed with pea gravel in a subsurface tile drain filter. This is it being constructed. This was a big bed filter. This was on a swine farm up in Holland, Michigan. We designed it to flow from the top down. We don't always do that. Some go from the bottom up. So here you see the bottom layer of drainage pipe. So this is going to there's the manifold that collects all the treated water. This gets backfilled with the metal shavings gravel mixture. And then you have your distribution pipe in there as well to distribute the water, tile water coming in. And then we covered this with a tarp and buried it. This is what it looked like when it was all done. They're not very exciting to show, underground ones after they're built. But this one used around 40 to 50 tons of that media mixed. And we used a flow control structure as a bypass in case if a filter ever clogs, if it can't handle a flow rate that exceeds its capacity. We use flow control structures to divert the water. Cost about $7,000. And we did this one with the Levy Corporation, Plant Tough, in cooperation with them. I mentioned before, you can combine these Pmobile structures with wetlands or wascobs, basically anywhere you impound water and then slowly release it. If it has high dissolved phosphorus, you can tack on to the end of it. It's pretty easy to plummet through a Pmobile structure of some sort. The advantage of this is that, having some sort of impoundment or a wetland, it drops out the sediment. So it removes the particulate P and it prevents clogging in the Pmobile structure. You don't want a lot of sediment going into a Pmobile structure. And the wetlands or storm basins, either way, they provide a hydraulic buffer for surface water. So you don't have to build a structure that treats 2,000 gallons per minute if you can store that water and then slowly bleed it out. You still need to treat it at a reasonable flow rate though. If you're doing this underground, a flow control, a water table control structure like an agri-drain can do this for tile drain. You just hold that water back in the field and then slowly bleed it through your filter. We do this all the time. And we also use those flow control structures to serve as an emergency bypass. You see here, if you can imagine, here's your tile coming down through, water gets stopped by the flow control structure and diverts it into the pea removal structure. But if it ever gets clogged up, we can't handle it, then the water height builds up in the flow control structure and then can continue on its way directly to the ditch untreated, serving as an emergency bypass. This is just standard now. Every tile drain structure filter we build now, we use one of those. So the cost, how much time do I got here? 10 minutes. Okay. The cost varies, as you could expect. It varies depending on the size. The bigger it is, the more it's going to cost. It depends on the site, depends on your pea removal goal. But ultimately, the cost is similar as a wastewater treatment when you look at it as dollars per pound of phosphorus removed, which ranges a huge amount with wastewater treatment plants, anywhere between like $50 and $700 per pound of phosphorus. We're in that range. A lot of the ones with the metal shavings and that, we're down more to like the $75 per pound, pretty good. And that's pretty good considering for a wastewater treatment, it's pretty easy. You got a single point source, high concentrations. That's easy to remove. Non-point, you've got very low concentrations. It makes it it's much more difficult to remove. You're fighting thermodynamics, and it's spread out over hundreds of acres instead of a nice single point. So it's worth more difficult to treat non-point. So I'm happy that we're still in that range. If you use a media that you can recharge, then every time you recharge it, you cut the cost in half at each regeneration. Like I mentioned before, metal shavings shows the most economic promise. From what I've seen so far, that's supposed to be a less than sign, not a greater sign, my mistake. Generally less than $10,000 for a typical structure with those. They like to use the metal shavings in Minnesota for their urban stormwater bioretention cells. Said it before, but don't use normal slag for treating subsurface drainage water unless you plan to replace the media annually. In fact, don't use it don't use any calcium-based pea sorption material for subsurface drainage. It works good for surface water, works good for silage runoff, does not work good for tile drainage. I'm going to skip this slide because I'd like to give you a super brief demonstration. I will say real quick that we are working on, finally, it's being built right now. COVID messed a lot of this up, but we've got a mobile demonstration unit being built that we can hook up and take around and show people how they work. So that's going to be completed this summer. There are training modules that's being produced by, it's a cooperative effort with the NRCS, ASABE, and ASA. We're making these training modules so people can become certified in design of pea removal structures. There's two separate modules. One's for the engineers, one for conservationists. The engineering one is obviously going to be a bit more involved. And so, like I said, people can then become certified in design or at least learn a tremendous deal about them in great detail. Those, I'm working on the last set of modules for those, and they should be done by the end of this year. The special issue on phosphorus removal structures in the Journal of Water. Okay. I don't know if we want to do any questions now, and then if we have time, I can show you a real brief demonstration with the P-Trap software. I'll leave that up to Dr. Helmers.
So yeah, actually, if we have a couple questions, maybe we can do a couple questions and then the demo. So people can either unmute themselves, type it in the chat box, raise their hand, however they want to alert me that they would like to ask a question of Dr. Penn. Maybe you can just transition to the model or the tool there, and folks can unmute if they have a question. I have a question, I guess. I mean, how you've been able to get the media there in Indiana. Have any that have gone in had trouble finding, appropriate media for use?
Yes, particularly with the metal shavings. They're there. Trust me, the steel shavings are there, but sometimes you got to ask the right people in the right way. I know it sounds crazy, but I drove by a metal recycling plant up near Fort Wayne for years, and I'd call them and they just ignored me. But Andrew Percival with NRCS. I don't know, he had a friend that worked there or something, but no problem. And ever since then, I've had a great relationship with them. And some of my friends in Minnesota, same thing. They they'd ask these places and they couldn't get the time of day, but you ask the right person the right way. And I don't know, that's probably been the one that we know they're there. We know there's steel shavings there, especially if you're anywhere near any kind of industry, where there's a lot of manufacturing, particularly in Northern Ohio. We're getting them from the GM plant. Northern Indiana, we're getting them out of Fort Wayne, where they got another GM plant, all kinds of other manufacturing places. They would normally be recycled to go back to the steel mill and be melted down. But as far as steel slag goes, you can get that anywhere. But there's other materials that work real well that are not available everywhere. Acid mine drainage residuals work really nice, but if you're not near anywhere they have mining, you're not gonna be able to find it. So, we get a pile of it in Western Pennsylvania and West Virginia, Eastern Ohio, where they're treating acid mine drainage. But, you're probably not gonna have that in Iowa, I'm guessing. So a lot of them are fairly available. And I always tell people, just start exploring and seeing what you got for byproducts, and you'll have something.
Just I looked while you were talking. I'm not sure it's listed for under a conservation practice standard in Iowa. So that may be something to work on. At least I didn't initially see it. So
I hope they get it added to there.
Yeah.
Okay. There's no more questions. Real quick, I just want to do a brief demonstration. This is the main. Here's your main page here for PTRAP. And there's a couple different areas to focus on. First, there's the site information. And in the site information, the most important thing is you need to have some idea of your average flow volume, annual flow volume. I should say average annual flow volume, and your average dissolved P concentration. Right now, what I have in here is the inputs that was given to me by Dr. Sapir, Dr. Kalina, when we were designing that blind inlet near Ames. And there are several all these help buttons, these information buttons. I tried to make them actually useful. So you click on them if you don't know what is being asked of you in a certain variable input. Just click on it, and you'll get an answer. So I tried to make this as useful as possible. The training videos will help even more. But anyway, so site information. Over here on the left, and then you have up here in the blue, you've got your PSM characteristics, physical characteristics, and then your phosphorus removal design curve. This is obtained from the flow through experiments, and most people are not going to know that information. So we've added a library here. It says PSM design curves database. You click on that, and there are hundreds and hundreds of curves organized by media and flow rate. Retention time and concentration, all that sort of thing. So you can just pick one and it'll populate it. If it's something, you need something that's not available, let me know, and I might be able to measure it for you. So anyway, in this case, we are going to, we're going to evaluate an existing bed structure. This software can do two things mainly. You can use it to design a structure to tell you how big, how much do I need to build this thing to meet my goals. That's design. Or you can evaluate an existing structure. That is, you can say, I'm going to build this. It's either in my mind or it's already built. And tell me what it's going to do. How is it going to perform? How much P is it going to remove? How long is it going to last? How much flow rate is it going to be able to handle? In this case, I'm going to demonstrate the evaluate an existing structure. I also separate them into ditch structures versus beds because ditches are unique hydraulically. So we're going to evaluate an existing bed structure. This is the blind inlet. So we've got our P removal curve for the material that we used in it. It's a steel metal shavings gravel mixture. This is our P removal curve, and we have our physical characteristics. In this bed, we know the size of it already. We know what pipe we have in it. Ultimately, the pipe in it drainage pipe is restricted to a single 6-inch diameter pipe set to a certain slope. One of those pipes is what's restricting it. And then we have the size of it. It's fit about 15 foot by 15 foot. And the media is approximately 30 inches deep. We have 30 inches of hydraulic head. Everything we need here will click go. And what you have is output down here. It tells you, again, this is for one that's already existing. So theoretically, we have about nearly 30 tons of media in this structure. And the peak flow rate that it can handle is around 154 gallons per minute. And at that peak flow rate, it will have a contact time, retention time of nearly 11 minutes. We also calculate the flow rate, what the flow rate is through the media versus what the pipe can handle. And obviously the least of those is what the unit will perform at. And then we have our pee removal table. Starting out first year, the cumulative pee removed as a percentage and also as a mass. So the first year, obviously you remove the most phosphorus, and with time, as you keep loading it with more and more phosphorus, it becomes saturated and it becomes less effective. So the first year you would remove theoretically around 86% of the load. At that point, it would remove almost 6 pounds of phosphorus. And then with time, you can see its efficiency decreases as it becomes saturated with phosphorus. And you can see this thing goes on, you get out to year 19 and you hit about 40% cumulative of removing 40% of the cumulative 19-year load, over 50 pounds of dissolved phosphorus. So this thing will last a good while, removing a lot of phosphorus. So you have that table on an annual basis. I'm going to show you one other thing. Same site, we're going to demonstrate the design. So now instead of evaluate, I'm going to design a new bed. Same site. However, let's say instead of building this blind inlet at the surface with the metal shavings, let's say we're going to build a subsurface filter to treat the tile drain water and the surface water, both. So in this case, I don't know exactly what the annual flow volume is. It's going to be more than just the 2 million gallons per year at the surface because we got tile drainage. So I just doubled it, 4 million gallons per year. And I lowered the P concentration because the subsurface drainage water is generally going to be a lot less than your surface flow. So I decreased it from 0.4 to 0.2 milligrams per liter. Same material, so same physical properties, same P removal curve. And then I put in my constraints. So I want this thing to have a retention time of at least 10 minutes. Why? Because my P removal curve was created at a retention time of 10 minutes. And I choose the P removal goal. I want it to remove 40% of the 5-year load of everything that flows through it in 5 years. And I want to use 4-inch diameter pipe to build this thing. And I want to set it at a slope of 0.5%. So other things in here, I'm not going to get into, but you can choose whether you want to design it as a top-down flow regime or bottom-up. We're doing top-down in this case. We have to indicate how much hydraulic head, whether we want that bed to remain saturated in between, or saturated with water, that is, in between events or not. In this case, I do not want it to be saturated in between events. Then we indicate how much area we're willing to sacrifice. I'm going to say we're willing to give up 30 foot by 30 foot. It's underground. And I say the maximum thickness of my bed I'm willing to make it is 60 inches. And the flow rate, I want to be able to handle at least 300 gallons per minute. It's a pretty high flow rate. And I have about 16 inches of hydraulic head to deal with. I'm assuming that I'm building this at the edge of the field, right before a ditch where that tile outlets into the ditch. So it'll be buried underground at the edge of the field, right before the ditch. So all those constraints, press go. All right. So it tells us how many tons we need to meet our goal. And you see there's a problem. See, there's a red flag. Flow rate through the structure and the retention time, the goal was not met. We wanted to have at least 300 gallons per minute and a retention time of at least 10 minutes. It was impossible. So it tells us it's impossible, but it gives you a suggestion. Estimated lifetime to meet both the target minimum flow rate and the retention time. It says, hey, increase your lifetime to at least 42 0.19 years, and you'll probably make it. So in other words, they're saying it's mathematically impossible to meet both your flow rate goal and your contact time, retention time, because those are opposed to each other, so as you can imagine. But make it bigger, add more pore volume, and you'll make it. So let's go back up and take their suggestion and increase our lifetime, desired lifetime to 43 years, and run it again. There we go. No red flags. So in order to meet all your goals, you had to make it bigger. Nearly 60 tons of the media, layered 16 inches thick, area equal to 30 foot by about 27.5 feet in area. Your 4-inch diameter pipe, you need 6 of them. And you do that, you meet your retention time goal and your flow rate goal. And here's the P removal that you would expect. So you can see we met our goal, 43 years, 40%. There we are, 43 years, 39.99%. At that point, you will remove about almost 115 pounds of phosphorus. And so obviously you start out removing more in the beginning, nearly 97% in the first year, and that decreases with time. So this can do a lot, this thing can do a lot more, but I just want you to get an idea. You can kind of piddle around with these things, change materials, adjust, target flow rates, size, things like that. And it's always trying to make the smallest structure possible because it's more economical. But there's a lot of different things you can piddle around on this and kind of hone in on the most economic and most efficient design for your particular site. So that, I'll shut up. Anybody have any questions?
I got one more that came in, and I think it kind of is related to what you were just talking about. I guess the question was how you determine when it needs to be replaced or recycled. And then I think you've kind of talked about this, but have any been in long enough to kind of evaluate if they are removing the approximate amount of phosphorus that you would expect based on your curves and the other output information you showed before?
Yeah. So I published a paper in Chemosphere in I think it's like 2016, where we took all the performance data we had from field structures and that we monitored and from pilot scale structures, and we used that and compared it to the model, to basically to the P removal curves essentially, and it worked. It works pretty good. I mean, it's no model's perfect, but it works pretty good, and I'll say it's as good as just like other models. It's as good as what you put into it. Your inputs are pretty accurate of reality, then it's going to predict it pretty well. Yeah.
Okay, maybe the last one here. There was one. Theoretically, is there an upper limit on the size of these P traps and the amount of flow or P they could treat? And if so, what would determine this upper limit?
Your upper limit is based on money and and what's feasible at the site, how much room you're willing to take up. I mean, there's some designer right now with some folks with the Great Lakes Commission where they want to treat a ditch that is a very large ditch that feeds the Sandusky that drains hundreds of acres. There's another one up in Michigan that drains. It's a county main. It's like a 24-inch drain, drains hundreds of acres. They want to build a structure for it. Well, that one's going to have to be pretty big, and it's going to be, several hundred tons of media. And well, is it worth it to them? Yeah, they want to do it. And, they're probably going to build it. So, it just depends. This is what I tell people: build them as large as you can, that is feasibly and economically possible, because they'll just remove more P and last longer.
All right. Thank you. Thank you so much, Chad. And it's great to know you'll be in Iowa in August for the Drainage Symposium. So there are probably a number of people on the seminar now that may be here. So hopefully they can listen to any presentations you have and also ask additional questions then. Again, thank you so much for your time. For everybody that attended, thanks for attending today. Feel free to go back and watch an archived webinar and keep on the lookout for announcements for the fall Iowa Nutrient Research Center seminar series. We're going to be trying to focus on some INRC funded research that's been done over the last 9 years. So with that, I hope everybody has a great rest of their Wednesday.